Dear ladies and gentlemen, hi together. It's really an honor and pleasure for me to present you the results of the Work Package 15 of the promotion project. The Work Package 15 will give you now information about the technology qualification of gas-insulated HVDC switchgear. Work Package 15, that means HVDC GIS technology demonstrator. And you will now see all about the prototype installation of compact gas-insulated switchgear and its testing and suitability for DC. My name is Riechert. Since more than 20 years I'm with ABB, now Hitachi ABB Power Grid Switzerland. I have conducted several product development projects in the field of gas-insulated switchgear high current systems and ultra-high voltage substations. Today I'm responsible for the development and product management of gas-insulated HVDC substation and circuit breakers, and also for partial discharge monitoring. Since 2017, I'm allowed to lead the Work Package 15 in the promotion project. We have divided this presentation into 3 parts, and I'm supported by Nadew Belda and Michael Gatzsche. Nadew Belda is innovation engineer with KEMA Labs. He's responsible for developing test methods and designing of test circuits for HVDC switchgear. He is also a task leader in Work Package 5 and Work Package 10 of the promotion project. Michael Gatzsche is R&D senior engineer for gas-insulated switchgear, and he is responsible for HVDC GIS and circuit breaker electrical contacts, high current systems, and instrument transformers, and he is a member of Work Package 15. To begin with, I would like to introduce the agenda. The first part of the presentation is about the Work Package 15 organization. In the second part, we will make some basic remarks about HVDC GIS applications and the question how to reduce the size of platforms with HVDC GIS. Later, we will give an overview about the prototype installation test, the test procedure and the test setup. And finally, we have prepared a short summary. The Work Package 15 has been formed to make a substantial contribution here. To increase the technology readiness level for HVDC GIS equipment to the highest level. To develop recommendations for specifying and testing of gas-insulated HVDC systems. To develop testing requirements, procedures and methods based on simulation analysis, real HVDC onshore and offshore experiences, and also based on the secret work. The focus of our task was to carry out a long-term tests of a full power HVDC GIS according to developed test requirements and procedures and using developed monitoring and diagnostic methods. Furthermore, we had the following tasks: to develop monitoring and diagnostic methods for HVDC to ensure a safe operation, to evaluate performance of SF6 alternatives, and finally, we wanted to improve models and develop the understanding of failure modes. In order to best fulfill our tasks, we have divided the work package into different task groups. The task group 1 has collected all the information needed to develop specification and to derive test requirements. For this purpose, the input from other work packages was used, mainly from Work Package 1, requirements for meshed offshore grids, and Work Package 4, HVDC grid protection systems. The task group was headed by sheet transmission. The task group 2 has been working on the development of monitoring and diagnostic methods and the applicability of SF6 alternatives, under the lead of the University of Delft. DNVGL and KEMA Labs were and are responsible for the long-term test. And in task group 4, valuable input for the standardization activities for HVDC GIS design, testing and application was collected and passed on to Work Package 11, harmonization towards standardization. The cooperation in Work Package 15 was characterized by a very high degree of openness, by scientific interest, great experience and close collaboration. The group was very well composed. It includes TSOs, a test laboratory, a research institute, a consultancy, a university, and a manufacturer, namely TenneT, SSE, KEMA Labs, Supergrid Institute, DNVGL, Delft University, and Hitachi ABB Power Grids. I would like to take the opportunity to thank all project partners for the interesting and exciting time and cooperation. And you can see here some pictures of our project meetings and conferences here. The new compact generation of HVDC GIS installation can be built with a much higher degree of compactness and significantly lower sensitivity to ambient factors than with air-insulated switchgear. The most obvious cost-saving potential can be found on offshore converter platforms, as shown here. Such converter stations are challenging during construction and installation. Some problems could be mitigated if the platform size could be reduced. By using HVDC GIS, the volumetric space of the switchgear installation itself can be reduced by 70 to 95%, which may result in a size reduction of 10% of the total platform. But until now, again, there has been only a little operating experience. Users intended to employ gas-insulated HVDC systems expect high reliability and long-term performance. This leads to the need for long-term tests on gas-insulated HVDC system in general. And the Work Package 15 has been formed to make here a substantial contribution to increase the technology readiness level of gas-insulated HVDC systems.
Based on the research of material characterization and the use of multiphysics simulation tools, the analysis of electrical field distribution is today possible with high precision. And it's possible to design insulators optimized for HVDC. With some additional changes at interface components and with the development of special current and voltage measurement devices, it was possible to design all required components. Just as in AC power systems, the HVDC GIS technology spans a number of switchgear components as shown here. Bus ducts and high voltage DC conductors, disconnect and earthing switches, bushings and cable terminations, current and voltage sensors, and surge arresters.
Based on development and research results as well as on service experience, the manufacturer has developed new artifact dielectric test procedures. All dielectric tests were already performed, like the DC withstand voltage tests, impulse tests, superimposed impulse tests, polarity reversal tests, dielectric tests under high load and zero load conditions, partial discharge measurement at AC and DC voltage stress. Moreover, new test procedures were developed, like the insulation system test or the prototype installation long-term test. Special type test standards for gas-insulated HVDC systems are not yet available today. CGRE Study Committee D1 has installed a working group, which should give recommendations on that, and Promotion Work Package 15 has also prepared the specification. There was also a demand from users and regulators for a full-scale demonstration of the technology readiness level of HVDC GIS. Such a full-scale demonstration, also called prototype installation test, was specified and executed as part of the promotion project. The 1.5-year-long test is now finished and verifies the overall performance of the manufacturer to produce and install HVDC GIS. Now Michael and Nadew will give more details about the prototype installation test.
What's the role of the prototype installation and the prototype installation test in the total product life cycle? When we have a new technology or a new product like HVDC GIS, when we as a manufacturer start with the R&D process, including simulations and development tests, the final goal of these efforts is to have a product that can be used in the field and that operates reliably for several decades. And to get there, classically, the R&D process finishes by performing all the type tests and completing them successfully. At least that's how we do it for an established technology like AC GIS. However, since HVDC GIS is a new technology, it's a bit more difficult. It starts with the type tests, as you heard from Nadew. They are a bit more complicated, and as of now, they're not even a fixed standardization. However, there are a lot of pre-standardization activities going on, and there are recommendations on testing, for example, from SIGRE, that recommend to include an insulation system test that combines dielectric and thermal stresses, that includes superimposed impulse voltage, and of course, that includes all the other AC GIS tests like temperature rise or short time withstand current. Because HVDC GIS is a new technology, even a completion of all these type tests would only put the technology readiness level of 6 out of 9, because as of yet we only have very limited operational experience with HVDC GIS. And to bridge this gap to the real in-service operation of the HVDC GIS, the prototype installation test is proposed. It is a full-scale demonstration, including specification and engineering of an HVDC GIS installation, the installation and commissioning of a quite large test pole, on-site long-term testing for more than a year with representative stresses, dielectric, thermal, mechanical. We have monitoring and diagnostic systems included in the test pole and third-party examination of all the steps. And a successful prototype installation test would verify the overall performance of a manufacturer to develop and produce and commission an HVDC GIS product. It is not a mandatory test, and it is also not a combination of all the type tests. And a successful prototype installation test would put the technology readiness level at 8 out of 9. So basically it would make it ready to be put in service. How can we specify an HVDC GIS? In promotion, we have done this, for example, with this case study where we have an HVDC link between Scotland and Shetland, and on this HVDC link we would add some offshore wind park. And to connect this offshore wind park, we could have a 3-terminal HVDC hub offshore, and there we would need a 320 kV HVDC GIS to reduce the size of the platform. And the proposal for the test pool was to use a GIS with the ratings you see on the right-hand table, and these ratings would fulfill the requirements for such a project. If we have a rated voltage of 350 kV, we have a superimposed lightning impulse voltage of 1050 kV, switching impulse of 950 kV, and 4000 amps rated current. The test pool itself looks like this. It is a rather large GIS ring with 2 SF62R bushings. These bushings are used to connect the high voltage from the test lab with the test pole itself. We have a second bushing to do some extended tests where we test the voltage withstand of an open disconnector gap. And the test pole has the form of a ring to be able to induce a heating current using conventional current transformers, so that we can also have thermal stress and the influence of the high temperatures on the dielectrics as part of the test. The prototype installation consists of all major components needed for such an HVDC hub. We have different gas compartments, we have all kind of modules, we have LX T-shaped modules. We have dismantling units. There are partition and support insulators, as well as disconnector insulating rods included as solid insulation. And we have DC capable instrument transformers, and we have the switching devices, the disconnector earthing switches and the fast acting earthing switch included. We have also monitoring systems for gas density. PD, we have an established UHF system, as well as more experimental optical, high frequency current transformer and magnetic antenna systems. We have the arc detection and enclosure temperature monitoring systems. In this time-lapse video, you can see the installation of the prototype installation test pool. We start by assembling the factory modules on their steel supports in the form of the basic ring. You can see that all the modules are connected, the cleanliness care is taken. Then we attach the bushings, configure the secondary technology, and then we actually start with the AC commissioning test that's now connected. The high voltage test passes, and after that the test pool is ready for the prototype installation test itself.
In this slide, I would like to present a test program that we have followed during this long-term test of HVDC GIS. Of course, the test program has been developed based on recommendations from SIGRE and also some wishes of end users. Before putting the HVDC GIS under long-term test, there are some steps that must be followed. In this case, it's a pre-test. In the pre-test, current is run through the bus duct to see, for example, the thermal cycle. How does the temperature of the enclosure varies depending on the current? And then there is a lightning and switching impulse applications, plus also partial discharge measurements under DC as well as under AC voltage. Also, lightning and switching impulse have been superimposed onto the DC voltage. That is what we call superimposed impulses. And also for a few hours of DC voltage application of both polarities. For example, 120 minutes positive polarity, another 120 minutes negative polarity, and so forth. After the pretest, which is basically a check procedure that HVDC GIS is ready for long-term test, then it is put under, of course, the actual test. And the actual test has 6 blocks, each block lasting for 60 days. And there are different load conditions. There is a zero load and a high load. And zero load means the DC GIS is put under a DC voltage, but there is no current running in the bus duct. The high load means the DC GIS is subjected to the DC voltage plus a current of 4000 amps running through the bus duct. So here you see zero load has had 2 blocks basically corresponding to positive and negative DC voltage. High load has been performed 4 times, twice for each polarity. And in between each block, at the end of one block, there are also other tests. For example, lightning impulse superimposed onto the DC, and close and open operations of switch disconnectors and earthing switch in that case, and also partial discharge measurements have been involved. And then, of course, the whole cycle has been successfully completed because at the moment of speaking, this test has been finished, and the main test blocks are followed by a load cycle. In the load cycle, the current is varied between zero load to high load, and this has been performed in two blocks, each block lasting for 15 days, which corresponds to each polarity. So 15 days positive polarity, 15 days negative polarity, while the load current is varying between 0 and 4000 amps. After the load cycle, there is subsequent test. Subsequent test is just to check the condition of the HVDC GIS after the test has been finalized. In this case, there are measurements of partial discharges under AC and DC conditions. There are also impulse applications, lightning and switching impulses, of course, also superimposed. Before I go into the test results, I would like to show you here the monitoring system that have been used. Of course, many monitoring system has been on board this HVDC GIS. For example, gas pressure check, partial discharge sensors have been put onto the device, arc detections in case if there is some flashover inside of the GIS tank. And also temperature, enclosure temperature has been measured at different locations. Here you see the thermocouples where they are placed, also trying to find out in comparison to the ambient. So there are thermocouples just placed in the ambient, in the neighborhood of the GIS to see the differences between the enclosure temperature and the ambient. There are disconnector and switch or using switch panels to show, of course, if they are in a closed or open position. Of course, the measurements of voltage and current temperature have been recorded, and this is available, and you will see that in the test results later. So a bit more about the three load cycles now with measurement results. This is taken randomly of, for example, measurements for 6 hours of temperature and current, for example, at high load, which is what you see on the left side, bottom graph, 4000 amps of current under 420 kV DC voltage. One thing I did not mention is a long-term DC voltage was chosen to be 420 kV. This is to compensate for the long-term long-term aging effect of HVDC GIS under real application, because this test lasts for 1 year. But to compensate for long term, the voltage has been increased by 20% more than the rated continuous voltage mentioned at the beginning. So here you see enclosure temperature being higher than the ambient temperature by a little bit more than 20 degrees Celsius. And on the right top, you see zero load testing block. Just for certain hours, of course, the temperature is ambient as you see it here, and there is no current, only the voltage has been applied, a voltage of 420 kV, in this case negative polarity. The third, which was in 15 days blocks, of course, the third test is a load cycle where current has been varied between zero load to high load as you see it. So a specific load profile for 24 hours has been specified, and that is followed to see the temperature of the enclosure, which you see it varying according to the current in this case. Some test results. Before the test results, you see the photo of the HVDC GIS under test. Well, on the right side of this photo, you see a DC source connected to the bushing of GIS. So 420 kV is supplied from there. And there is an impulse generator on the right side, which can generate lightning as well as switching impulse. This has been superimposed through a spark gap. There are different methods. We use the spark gap method. For example, a capacitor coupling method could be used. And on the left, you see test results. Of course, lightning superimposed onto the DC voltage and switching superimposed onto the DC voltage of both polarities. That's what you see on these graphs. And of course the test circuit is shown on the top right. Well, on many occasions, of course, people are invited to see the test when the test object is live or under stress. Of course, it was one of the purpose of promotion to demonstrate, to show to the different stakeholders what's going on, and this photo was taken when a lot of people were invited to take part in demonstration of HVDC GIS. Well, a bit about test results. Of course, all the different stages of testing, the pre-tests, of course, a load or the blocks of load tests, and subsequent tests have been successfully completed. At the pre-test, as I mentioned, there are different measurements, partial discharge measurement, also application of lightning and switching impulses. During the long-term load cycle tests, twice zero load and 4 times high load has been performed, and also twice load cycle has been performed, which were successfully completed. And of course, subsequent tests to check the condition of the test object has been performed, which was also included AC, DC, partial discharge measurement, lightning impulse of different polarities. And then of course visual inspection during disassembly, which showed no trace of any kind of damage, and this shows a complete successful demonstration of HVDC prototype, GIS prototype installation.
Let me now summarize the key technical conclusions from Work Package 15. The technology readiness level is increased from 6 to 8 for an HVDC gas-insulated system. Recommendations for specifying gas-insulated HVDC GIS were developed. Testing requirements, procedures, and methods were developed based on simulation analysis, on real HVDC onshore and offshore experiences, and based on the C-GRE work. Long-term testing of full-power HVDC GIS were carried out according to the developed test requirements and procedures. The results were used to improve the models and develop understanding of failure modes. Work Package 15 are aligned with and have contributed to ongoing pre-standardization of HVDC GIS in C-GRE and in ISC. The members of Work Package 15 are also very active in standardization and pre-standardization groups, and we have also initiated new pre-standardization work. For instance, the joint working group B1, B3, D1, 79 from C-GRE, a new working group about recommendations of directive testing of HVDC gas-insulated system cable sealing ends. Moreover, we had a close cooperation with the C-GRE joint working group dielectric testing of gas-insulated HVDC systems, and with the D163 partial discharge detection under DC voltage stress, as well as with the D167 dielectric performance of new non-SF6 gases and gas mixtures for gas-insulated systems. Also, in the ISC standardization activities, the Work Package 15 members are involved, especially in ISC TC17 and TC17C and TC99. For instance, in the Working Group 6, Common Specification for DC Switchgear, as well as in Working Group 42, DC gas-insulated switchgear assemblies. I want to mention also that Work Package 15 has prepared in total 8 reports. 4 reports are already published. The document on recommendations for specifying DC GIS systems, a document on test requirements, procedures and methods, a report on DC GIS diagnostic and monitoring tools and methods, as well as a report on characteristics of a PD alternative gas, comparison with SF6. 4 more reports are currently under review, and you will find all the report latest in September on the ProMotion website. And again, summarizing from the tests, it can be expected that HVDC GIS components will have equally long lifetime as known from HVAC GIS. Using GIS technologies, the space requirements for a HVDC switchgear can be reduced by 70 to 95%, leading to lower costs. And again, I would like to take the opportunity to thank all project partners for the interesting and exciting time and cooperation. Thank you very much for your attention.